For the unit Thermodynamics, in previous lecture we discussed applications of enthalpy of combustion, calorific value of fuels and foods, enthalpy of solution or heat of solution, and enthalpy of neutralization or heat of neutralization. In continuation, today we are going to discuss enthalpies of physical change, which will include enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Then we will discuss Hess's law, which is also the law of constant heat summation. After it, applications of Hess's law, determination of lattice energy, and influence of temperature on the heat of reaction or Kirchoff's equation. First, we are going to discuss enthalpies involved in physical changes. When a substance changes from one physical state to other, enthalpies are involved or heat is evolved or absorbed. First of all, we are going to discuss enthalpy of fusion. Enthalpy of fusion is equal to the heat change which is involved during the of a solid change its liquid state at its melting point. Enthalpy of fusion of a substance is equal to its latent heat of fusion multiplied by the molecular mass of the substance. Enthalpy of fusion gives an idea about intermolecular forces operating in a solid. Enthalpy of fusion for ionic substances is greater than covalent substances because intermolecular forces operating in ionic solids are greater than the intermolecular forces operating in covalent solids. Actually, covalent solids are held by weak van der Waals forces. For example, enthalpy of fusion for water is equal to 1.44 kilocalories and enthalpy of freezing for water will be equal to minus 1.44 kilocalories. Now we will discuss enthalpy of vaporization. Enthalpy of vaporization is the heat change when 1 mole of the liquid substance gets converted to its gaseous form or vapor form at its boiling point. Enthalpy of vaporization gives an idea about the intermolecular forces in the liquid state. For example, enthalpy of fusion for water is equal to 10.5 kilocalories and enthalpy of condensation for water will be equal to minus 10.5 kilocalories. Now, enthalpy of sublimation. Sublimation is the process in which the solid state of a substance directly changes to its vapor state. The enthalpy of sublimation is the heat involved when 1 mole of the solid is directly changed to its gaseous or vapor state. For example, enthalpy of sublimation for iodine is equal to 14.9 kilocalories. Normally, enthalpy of sublimation is equal to the sum of enthalpy of fusion plus enthalpy of vaporization. Hess's law or Hess's law of constant heat summation is an important law in thermochemistry. This law was given by Hess in 1840. According to this law, if a reaction is made to occur in various steps or in one step, the total enthalpy change will remain same. It means the enthalpy does not depend on the intermediate steps. Let a substance A is converted to D in 3 steps. The enthalpy change from A to B is delta H1, from B to C it is delta H2 and from C to D it is delta H3. Now, the total enthalpy change from A to D will be equal to delta H, which is equal to delta H1 plus delta H2 plus delta H3. Let this delta H1 plus delta H2 plus delta H3 is denoted by delta H steps. Now, if D is converted back to A in single step directly, then heat involved in this process is taken to be equal to delta H direct. According to thermodynamics, delta H direct plus delta H steps must be equal to 0. That is, delta H direct will be equal to delta H steps with opposite sign. If it is not so, then some heat must be evolved or absorbed during one cycle, which is not possible according to first law of thermodynamics. Hence, the only possibility left is that delta H direct is equal to delta H steps. Hess's law can be verified with the help of some examples. Formation of carbon dioxide from carbon can take place in two ways, in single step or in two steps. In first method, it is prepared in single step. Carbon is directly converted to carbon dioxide as carbon solid plus oxygen gas, giving carbon dioxide gas. Delta H for this reaction is minus 393.5 kilojoule. In second method, we are preparing carbon dioxide in two steps. In first step, carbon is converted to carbon monoxide, and its second step, carbon monoxide gets converted to carbon dioxide. For first step, when carbon gets converted to carbon monoxide, the delta H is equal to minus 110.5 kilojoules, and when carbon monoxide gets converted to carbon dioxide, delta H is equal to minus 283.0 kilojoules. Total enthalpy change from carbon to carbon dioxide, that is delta H, will be equal to minus 393.5 kilojoule, which was the same enthalpy as was used in single step. This example you can see graphically also. When carbon in graphite form plus oxygen gives you carbon monoxide, delta H is minus 110.5 kilojoules, and when carbon monoxide further reacts with oxygen to give carbon dioxide, delta H is minus 283.0 kilojoule. But if carbon and oxygen reacts directly to give carbon dioxide, then delta H is minus 393.5 kilojoules. Hence, Hess's law is verified. Now we will discuss some conclusions of Hess's law. The heat of formation of compounds is independent of the manner of its formation. The heat of reaction is independent of the time consumed in the process. The heat of reaction depends on the sum of enthalpies of products minus sum of enthalpies of reactants. And the thermochemical equations can be added, subtracted or multiplied like algebraic equation. For thermochemical calculations, some points must be remembered. First of all, write down the balanced thermochemical equation. For example, if you want to calculate the heat of formation of methane, then write down the equation carbon solid plus 2H2 gas giving CH4 gas. Now you have to calculate delta H for this reaction to calculate the heat of formation of methane. Now try to obtain the required equation from the given data. This can be done in two ways. First one is by adding, subtracting or multiplying the given equations with some suitable numbers, and the second one using the enthalpies of products and reactants and using the equation delta H of reaction is equal to total enthalpies of products minus total enthalpies of reactants. For thermochemical calculation of heat of formation of substances, the heat of formation of elements in their standard state should be fixed as equal to 0 at 25 degrees Celsius and 1 atmosphere pressure. There are various applications of Hess's law of constant heat summation. First one is, we can calculate the heat of formation of those substances which cannot be prepared directly from their constituent elements. This can be done by using the heat of combustions of various substances. For example, Calculate the heat of formation of acetic acid from the following data. CH3COOH liquid plus 2O2 gas giving you 2CO2 gas plus 2H2O liquid. Delta H for this reaction is equal to minus 207.9 kilojoule. This is equation number 1. Second equation is carbon solid plus oxygen gas giving you carbon dioxide gas. Delta H for this reaction is equal to minus 94.48 kilojoules. The third reaction is H2 gas plus half O2 gas giving you H2O liquid. Delta H for this reaction is minus 68.4 kilocalories. This calculation can be done by two methods. For first method, we have to write the required equation as 2 carbon solid plus 2 H2 gas plus O2 gas giving CH3COOH liquid. Now, delta H for this reaction has to be calculated to calculate the heat of formation of acetic acid. This equation can be obtained by multiplying equation 2 by 2 and also equation 3 by 2 and adding both and finally subtracting equation 1. We will get 2 carbon plus 2 O2 plus 2 H2 plus O2 minus CH3COOH minus 2 O2 giving you 2 CO2 plus 2 H2O minus 2 CO2 minus 2 H2O. Cancelling same terms, we will get the required equation. Hence, delta H for CH3COOH formation will be equal to 2 into minus 94.48 plus 2 into minus 68.4 minus 207.9, which will be equal to minus 188.96 minus 136.8 plus 207.9, which is equal to minus 117.86 kilocalories. Now, there is alternative method also for this calculation. From equations 2 and 3, you can get enthalpy of carbon dioxide or enthalpy of formation of carbon dioxide equal to minus 94.48 kilocalories and enthalpy of H2O or enthalpy of formation of H2O equal to minus 68.4 kilocalories. Enthalpy of oxygen is equal to 0 because the enthalpy of free elements is taken to be 0. Delta H of equation 3 will be equal to enthalpies of products minus enthalpies of reactants. Therefore, minus 207.9 will be equal to 2 into minus 94.48 plus 2 into minus 68.4 minus delta H CH3COOH liquid. Therefore, delta H for liquid acetic acid will be equal to minus 188.96 minus 136.8 plus 207.9 equal to minus 325.76 plus 207.9, which will be equal to minus 117.86 kilocalories. Hess's law of constant heat summation can also be used to determine the enthalpies of reactions which are extremely slow and to calculate the enthalpies of transformation of one allotropic form to another allotropic form. For example, if we want to calculate the enthalpy of change of rhombic sulfur to monoclinic sulfur, it can be done on the data based on the heat of combustions or enthalpy of combustions of rhombic sulfur and monoclinic sulfur as rhombic sulfur plus oxygen gas giving you sulfur dioxide gaseous. Delta H for this reaction will be equal to minus 291.4 kilojoules. And if monoclinic sulfur has been taken, then monoclinic sulfur plus oxygen gas giving you sulfur dioxide gaseous, delta H for this reaction will be equal to minus 295.4 kilojoule. Hence, heat of combustion for rhombic sulfur is minus 291.4 kilojoules and heat of combustion for monoclinic sulfur is equal to minus 295.4 kilojoules. Subtracting equation 2 from 1, we will get rhombic sulfur minus monoclinic sulfur plus oxygen gas minus oxygen gas, giving you sulfur dioxide gases minus sulfur dioxide gaseous. So, delta H for this reaction will be equal to minus 291.4 minus 295.4, and the required equation will be converted to rhombic sulfur, giving you monoclinic sulfur, and delta H for this reaction will be equal to 4.0 kilojoules. Therefore, the heat of transition of rhombic sulfur to monoclinic sulfur will be equal to 4.0 kilojoules per mole. Hess's law of constant heat summation can also be used to calculate resonance energy, as resonance energy is equal to observed heat of formation minus calculated heat of formation. Some other applications of Hess's law of constant heat summation are for the determination of bond energies by using the expression delta H reaction equal to sum of bond energies of reactants minus sum of bond energies of products. Lattice energy can be determined with the help of Born-Haber cycle. Lattice energy is the heat evolved when 1 mole of the solid substance is formed by the combination of its constituent ions in gaseous form, that is by the combination of gaseous cations and gaseous anions. Normally, lattice energy is represented by symbol U, and it is negative because it is heat evolved. For example, A plus gaseous plus B minus gaseous gives you AB, which is a solid, plus energy released here is equal to the lattice energy of AB. As it is very difficult to calculate lattice energy directly, hence an indirect method based on Born-Haber cycle is used to calculate lattice energy. Born-Haber cycle is based on Hess's law of constant heat summation. Let us take an example of the formation of solid sodium chloride from solid sodium and gaseous chlorine. Schematically, this formation can be represented as solid sodium and gaseous chlorine can combine directly to give solid sodium chloride, and in this formation the heat used or heat involved is equal to Q. This combination of sodium and chlorine to produce sodium chloride can happen in various steps also. In first step, solid sodium has to be converted in gaseous sodium by using the delta H sublimation of solid sodium. The heat of dissociation for chlorine will be required to dissociate chlorine molecule to chlorine atom, as for 1 mole of chlorine, D will be equal to heat of dissociation, hence half of D will be used for half mole of chlorine. Now, gaseous sodium has to be converted to Na plus gaseous. This can be done by using an energy equal to ionization energy or ionization potential of sodium. Gaseous chlorine can be converted to Cl minus ion. During this process, an energy equal to electron affinity of chlorine will be liberated. This electron affinity will be negative. Now, gaseous Na plus gaseous Cl minus will combine to give solid NaCl by liberating an energy equal to lattice energy, which is represented by U. This lattice energy has also been taken to be negative because it is also the energy evolved. Hence, the total energies involved in these 5 steps will be equal to delta H sublimation of sodium, half of dissociation energy of chlorine gas plus ionization energy or ionization potential of gaseous sodium plus electron affinity of chlorine. This electron affinity has to be negative plus lattice energy of sodium chloride. This lattice energy must also be negative. Therefore, according to Hess's law, Q will be equal to delta H sublimation plus half of dissociation energy plus ionization potential plus electron affinity plus lattice energy. By using this expression, lattice energy can be calculated if all other energies are given. We can have a look on an example. Calculate the lattice energy for the reaction lithium plus gaseous plus Cl minus gaseous, giving you lithium chloride solid. The given data is delta H sublimation for lithium is equal to 160.67 kilojoules per mole. Half of dissociation energy for chlorine is equal to 122.17 kilojoules per mole. Ionization potential for lithium is equal to 520.07 kilojoules per mole. Electron affinity of chlorine is equal to minus 365.26 kilojoules per mole, and delta H naught formation for solid lithium chloride is equal to minus 401.66 kilojoules per mole. Now, applying the equation, Q is equal to delta H plus half T plus IP plus electron affinity plus lattice energy, and substituting the respective values, we will get minus 401.66 equal to 160.67 plus 122.17 plus 520.07 minus 365.26 plus U, which is equal to lattice energy. Hence, U, that is lattice energy, will be equal to minus 839.31 kilojoules per mole. Now, we will discuss the effect of temperature on heat of reaction, which will be given by Kirchoff's equation. First, let us consider the reaction at constant pressure. At constant pressure, delta H is equal to H of products minus H of reactants, and we know that delta H is equal to Cp dt. Now, integrating this equation within proper limits, we will get integral of d delta H within the limits T1 and T2 will be equal to delta Cp integral of dt within the limits T1 and T2. Now, integrating this equation, we will get delta H at T2 minus delta H at T1 equal to delta Cp T2 minus T1. Rearranging this equation, we will get delta H T2 minus delta H T1 upon T2 minus T1 equal to delta Cp. This equation is known as Kirchoff's equation. It is used to calculate the heat of reaction at a temperature provided the heat of reaction at some other temperature is given. Change in heat of reaction due to per degree change in temperature is equal to delta Cp, which is the change of heat capacities in products and reactants. Delta Cp will be equal to heat capacities at constant pressure of products minus heat capacities at constant pressure of reactants. If we consider the reaction taking place at constant volume, then Kirchoff's equation will become delta E T2 minus delta E T1 upon T2 minus T1 equal to delta Cv. That is, at constant volume, the heat change per degree change in temperature will be equal to delta Cv will be equal to Cv of products minus Cv of reactants. Here is an application of Kirchoff's equation. The heat of reaction half H2 plus half Cl2 giving you HCl at 27 degrees Celsius is minus 22.1 kilocalories. Calculate the heat of reaction at 77 degrees Celsius. The molar heat capacities at constant pressure at 27 degrees Celsius for hydrogen, chlorine and HCl are 6.82, 7.70 and 6.80 calories per mole respectively. Here the required equation is half H2 plus half Cl2 giving HCl. Delta H for this reaction is given as minus 22.1 kilocalories. Now delta Cp will be equal to heat capacities of products minus heat capacities of reactants, which is equal to 6.80 minus half into 6.82 plus half into 7.70, which is equal to 6.80 minus 7.26 equal to minus 0.46 calories, or we can say that minus 0.46 multiplied by 10 to the power minus 3 kilocalories. As we are given that T2 is equal to 77 degrees Celsius, which is equal to 350 Kelvin, and T1 is 27 degrees Celsius, which is equal to 300 Kelvin. Hence, T2 minus T1 will be equal to 50 Kelvin. Now, we have to use the equation delta H2 minus delta H1 equal to delta Cp multiplied by T2 minus T1. Substituting these values in Kirchoff's equation, we will have delta H2 equal to minus 22.1 plus minus 0.46 multiplied by 10 to the power minus 3 multiplied by 50, which is equal to minus 22.1 plus minus 0.023 equal to minus 22.123 kilocalories. Therefore, heat of reaction at 77 degrees Celsius will be equal to minus 22.123 kilocalories. In the end, let us revise what we have learnt today. Today, we defined various enthalpies of physical changes or phase changes, which included enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Hess's law of constant heat summation, applications of Hess's law, determination of lattice energy by Born-Haber cycle, and influence of temperature on the heat of reaction, or we can say Kirchoff's equation. In continuation, in next lecture, we will discuss the experimental determination of heat of reactions.